Okay, so the main goal of this section will be to compute various probabilities for Brownian motion and Brownian bridge using the so-called reflection principle for Brownian motion. But before we get to that, we need to discuss the so-called strong Markov property, which we will also need in the next section. Okay, so we begin with some probability space with a sigma algebra F and probability P on it. Okay, and on this probability space we consider a Brownian motion, which we will now denote Wt. And we will also consider an increasing sequence of sigma algebras, which we will denote by Ft. They will be also indexed by this time parameter t greater or equal than 0, which will be sub-sigma algebras of the sigma algebra on this probability space. And we'll assume that the following properties are satisfied. So first of all, as I said, this will be an increasing sequence, so Ft will be inside Fs whenever t is less than or equal than s. The second property is that the Brownian motion will be measurable on this sigma algebra. So in other words, if we consider a sigma algebra Bt generated by a Brownian motion up to time t, this will be inside this sigma algebra Ft for all t. Okay, and the last property will be that the increments after any fixed time of the Brownian motion are independent of that sigma algebra at that time. So if we consider the increments after some fixed time t, right, this whole process after that time, or the increment process, will be independent of the sigma algebra Ft. Okay, and this is true for any fixed t. Okay, maybe let's give an example why we would be interested to consider a sequence of sigma algebra rather than these sigma algebras generated by the Brownian motion itself. Well, this is simply to include some additional data. Okay, for example, if we have some sigma algebra A, which is independent of the Brownian motion, or independent of the sigma algebra generated by the Brownian motion, then we can simply include this sigma algebra, so we can define Ft to be a sigma algebra generated both by the Brownian motion up to time t and this independent sigma algebra A. Okay, and then it's easy to see that this satisfies the properties 1, 2, 3. And so in the results that we'll consider now, what we really need is that the increment of the Brownian motion after some fixed time t is independent of these sigma algebras. And next, we define the stopping time, which is the same definition as in the case of random walks, with the only difference that the time now is a continuous variable. Okay, so a random variable tau, which is non-negative, is called the stopping time. Okay, of course, this definition is relative to the sequence of sigma algebra. So with respect to this sequence of sigma algebra Ft, if the event that's this time tau is less than or equal than t belongs to the sigma algebra Ft, okay, and this is true for all t. One example of this that will come up a lot in this section is an example of the heating time. The heating time tau c, it will be the first time when the process W hits this level c. Okay, and this will be defined for c typically not equal to 0. And indeed, to see that this is a stopping time according to that definition, right, we just need to check that this event is in Ft. And so we can rewrite this event in terms of the Brownian motion itself by saying that for every level x below c, there exists a time s before t, so that the Brownian motion at time s will be above x. Right? So by continuity, in order to hit this level c before time t, you have to cross every level x less than c before time t. So you can write it like this, and of course here you can restrict both the level and the time to be rational, so that here we have a countable union and countable intersection. Okay, so this property, or this representation here, is just by continuity of the process. Okay, and now once you represent it in this form, of course it's clear that this last event here is in Fs, which is inside Ft, so this whole thing is inside Ft. And then, just like in the case of the random walks, we will need a definition of this sigma algebra up to the stopping time. Okay, so we'll define a sigma algebra of events up to the stopping time tau, and we'll denote that sigma algebra by f tau. It will be all measurable sets in our space, such that the part of the set on the event when the stopping time is less than t belongs to the sigma algebra ft. And this is true for all t. Very similar definition to what we have seen for random walks before. And now, given these definitions, our first main result will be the following strong Markov property of the Brownian motion. Okay, which will state the following. Namely, on the event that the stopping time is finite, okay, in words we can say the following, that the following increment process will denote it by W prime. Okay, so it will be the process of the increments after the stopping time tau, and so it will be again indexed by non-negative t. Okay, and this process, first of all, it's independent of the sigma algebra up to the stopping time, and moreover, this process is equal in distribution on the Brownian motion on this event. Okay, and more precisely, okay, we can write that the expectation of the indicator that this process of the increments after the stopping time belongs to some set A, now indicator of some set B, which will be in the sigma algebra f tau, on the event that the stopping time is finite, will be equal to the expectation of the indicator that the Brownian motion belongs to the set A, and by independence this will be just times the expectation of the indicator of the set B on the event that tau is less than infinity. Okay, where first of all this set B will be inside the sigma algebra up to the stopping time, and the set A will be any Borel set in the space of continuous functions, okay, with the metric that metrizes uniform convergence. Okay? So our Brownian motion and the process of these increments, they are by definition continuous, so they belong to the space of continuous functions. So here we consider events which are Borel in that space. Okay, so the statement is very similar to what we have seen in the setting of random walks, and the proof will essentially be identical after some preliminary approximation argument. Namely, we notice that in order to prove the above identity, we can reduce it, we can replace the first indicator by a continuous function of some finite dimensional projection on our process. more precisely, first of all, because the Borel sigma algebra on the space of continuous functions, as we have discussed before, it's just an intersection of the space of continuous functions with the cylindrical sigma algebra on the space of all functions on the half line. So A here is the cylindrical algebra, or cylindrical sigma algebra. So by Dynkin's theorem or by monotone class theorem, this means that it's enough to prove the above identity for sets in the algebra that generates the sigma algebra. So in other words, it is enough to consider these sets A in the statement of the theorem above inside the cylindrical algebra. Okay, or more precisely, we can take any d and any finite set of times t1, td, and also take a set C, a Borel set in Rd, and consider the indicator of the following form. So indicator that the process belongs to a set A. When set A is a cylinder with this base C, right, it just means that you consider the indicator that the process at this finite collection of times t1, td belongs to the set C. So in the above statement, you can only consider indicators of this form. Now, moreover, by Dynkin's theorem, again, it's enough to consider sets C which are open. So in fact, instead of Borel, if you prove this only for open sets, the equality of these two sides or these two integrals will be true for all sets. And then, as we often did in the chapter on convergence on metric spaces, you can approximate an indicator of an open set by bounded Lipschitz functions. So as a result, it's enough to prove the statement when the indicator is replaced by bounded Lipschitz, or let's just say continuous bounded function. So after this discussion, we see that it's enough to prove the following. It's enough to prove that the expectation of some function evaluated on times t1, td of this process w prime, the process of the increments after the stopping time, indicator of some set in the sigma algebra up to the stopping time, on the event that tau is finite. Okay, this should be equal to the expectation of the same function on the Brownian motion at these times times the expectation of this indicator on the event that tau is finite. So if we can prove this, this will prove the strong Markov property above. And in order to prove this, and here comes the main idea of the proof really, the main idea is the following, that you discretize your stopping time by rounding it up to a dyadic. So in other words, you take some 2 to the n times your stopping time. Okay, you round it down and then add +1 and divide by 2 to the n. Right? So first of all, since you round it up, this will be bigger or slightly bigger than your stopping time. And in particular, when the stopping time is in between some dyadic of the form k over 2 to the n and strictly less than k plus 1 over 2 to the n, right? Our definition, the fact that we round up, means that this will be rounded up to k plus 1 over 2 to the n. The reason we round up is because, as we notice right away, that this makes this discretization tau n also a stopping time. Okay, and to show this, we need to show that the event tau n less than or equal than t is in the sigma algebra Ft. And for this, of course, what we'll do is we'll find the dyadic interval where this t belongs. So let's say L divided by 2 to the n is less than or equal than t, and strictly less than L plus 1 over 2 to the n. So in other words, you find L such that t is in this interval. Well, because tau n is dyadic, right, that means that tau n must be less than or equal than L over 2 to the n. And since tau n was rounding up of the stopping time tau, that means that the stopping time tau must be strictly less than L over 2 to the n. So I want to conclude that this is now in the sigma algebra F at time L over 2 to the n, but because in the definition the inequality was not strict, while here the inequality is strict, well, this really doesn't matter, because the fact that tau is strictly less, you can just write it as a union over rational strictly less than L over 2 to the n of the same event that tau is less than or equal than that rational, right? And then by definition now, with the non-strict inequality, this is in FQ, which is by the monotonicity is in FL over 2 to the n. So this implies that with the strict inequality, our event is also in F with that time, which in particular is inside f of t, because t is greater or equal than L over 2 to the n. Okay, and once we make this observation that this rounding up discretization is also a stopping time, the rest of the proof is just like in the setting of random walks, where you simply consider all possible values for the stopping time, which is now discrete. In other words, what we want to prove, recall that we are looking at this expectation of some continuous bounded function on the increment, so I'll write this a little bit more explicitly now. Okay, and in order not to write this function at finitely many times, I'm going to denote this by E of tau. Okay, so let's view this as a function of the stopping time tau. Okay, and then I want to go to discretization. So in other words, I want to consider the same quantity or the same integral as above, just that time tau n instead of tau. Okay, and we see, of course, that immediately, because tau n converges to tau almost surely, in fact, on the indicator that tau is bounded, they are within 1 over 2 to the n to each other. Of course, this implies that these integrals will also converge as n goes to infinity, right? And this is just by continuity of the process with respect to time. So everything here depends continuously on tau, and the function f is bounded and continuous. But once we have this discrete stopping time, then we'll simply break this integral into all the possible values that it can take. In other words, we take tau to be of the form k over 2 to the n on the indicator that, right, this stopping time tau n is k over 2 to the n. And here I'm not writing the indicator that tau is finite, because tau is finite if and only if this tau n is finite. Now in this sum, once we break it into these pieces, now we take a look at this event b intersected with the event that tau is equal to k over 2 to the n. If we rewrite this second event in terms of the original stopping time, namely that this means that the original stopping time should be between k minus 1 over 2 to the n and k over 2 to the n. Here we of course recall that we chose the event B to be in the sigma algebra up to the stopping time. And by the definition, so if we rewrite this intersection as B intersected with the event that tau is strictly less than k over 2 to the n, k minus B intersected with the event that tau is strictly less than k minus 1 over 2 to the n. By definition, this event here should be in the sigma algebra f up to time k over 2 to the n. Okay, that was by the definition of the sigma algebra f tau. Now again, the only difference here is that we have strict inequality, while in the definition the inequality was not strict, but then we use the same trick as we just did, right? That the strict inequality can be written as the fact that tau is less than or equal than any rational number up to this time. Okay, so this property also holds with the strict inequality. And of course, the same thing here, this will be in the sigma algebra up to time k minus 1 over 2 to the n. So this whole thing is in the sigma algebra up to time k over 2 to the n. And in particular, it implies that this function e at the time k over 2 to the n, right, which remember it was just a function of the increments. So it's a function of the increment after time k over 2 to the n. And by the properties of the Brownian motion, of course, this is independent. These increments, they are all independent of f k over 2 to the n. Or more precisely, it's by the property 3 that we assumed above. So as a result, in the above sum, so we stopped here by decomposing this integral into the sum of integrals. The event in these two indicators is independent of this function e evaluated when the stopping time is k over 2 to the n. So now we can write it as a product of expectation by independence. And so we can rewrite this as the sum over k, expectation of this function at k over 2 to the n times expectation of the indicator of the set B, an indicator that tau n is k over 2 to the n. And finally, we use stationarity of the Brownian motion to say that this first integral, it doesn't matter at which time it's evaluated. So the expectation here, you can start at time 0, so the increments, their distribution will only depend on the size of the increments. And so we are just left with sum over k of the expectation of these two indicators. Okay, and of course the sum is just the indicator that the stopping time is finite. Okay, and that's exactly what we wanted to prove, because this first term is exactly that function f, only now evaluated on a Brownian motion starting at time 0, just like we wanted. Now, in the next section, we will use this result exactly in this form, but in this section, we'll use a slight modification of it. So, in particular, when we consider in the above result these indicators that the process of increments belongs to some set A, or the Brownian motion belongs to some set A, we'll be actually looking at the situations when the set A depends on the stopping time as well. Right, so here we considered a set A to be some Borel set on the space of continuous functions. But in our examples, it will also depend on the stopping time tau. Okay, and so reducing to the above statement, it can be a bit subtle. So you have to see how these sets depend on tau. So instead of using this statement, it will actually be more convenient to prove a specific version of the statement that will be needed in the applications in this section. Namely, we'll consider the following two operations. So the first one, I'll call it restart. Okay, and this is will be the following. So we'll consider some fixed time s first, and then we define the Brownian motion with independent restart. So I'll denote it by index I. It will be a function of time t, but it also will depend on this parameter s here. And by definition, this will be the following. This will be our process, or our Brownian motion up to time s. Okay, and then after time s, okay, we started at this position, but instead of the increment wt minus ws, we just restarted by some different process with a time t minus s, okay, on the indicator when t is bigger than s, okay, where this w tilde is a Brownian motion, okay, independent of all the sigma algebras that we have considered so far. So in other words, independent of ft for all t. In particular, if necessary, you can just extend your probability space by adding another coordinate, for example, a space of continuous functions, and you can just place this Brownian motion as a coordinate on the product space. Okay, and clearly this definition gives us again a Brownian motion. Okay, we just replace the independent increments after time s by an independent copy of a Brownian motion. And the second operation that we'll consider, well, it can actually be reduced to this, but it's just more convenient to consider them both at the same time, and this will be the operation of reflection. So we'll simply reflect the increment of our Brownian motion after this time s. So we'll define this process w, and I'll give it an index r here for reflection as a process of time t, okay, for this given parameter s. Again, it will be wt up to time s, and then after time s, instead of adding the increment wt minus ws, we are just going to subtract it. So we are going to reflect it around the axis. Okay, so that's on the indicator when t is bigger than s. Okay, so we define these two operations, and clearly both give us a Brownian motion because the time s is fixed, so all the properties of the Brownian motion are still satisfied. And of course, these modifications, they are still continuous as a function of time. In fact, notice that both are actually continuous as a function of both t and s, right? Because the only discontinuous part is the indicator, but the jump occurs when t is equal to s. And at t equal to s, the increment that we add is 0 in both cases. So w tilde at 0 is 0, and wt minus ws is also 0 when t is equal to s. So it's easy to see that actually this is continuous in both variables, which will be useful to us in a second. And as I said, clearly these processes, either wi for a fixed s viewed as a function of t, okay, is equal in distribution to this second process wr when you view it as a function of t for a fixed s. Okay, both are Brownian motions, so both are equal in distribution to a Brownian motion. And so a version of the strong Markov property that we'll prove now, which we'll call reflection principle, will be that actually if you replace a fixed time s by a stopping time, that this equality in distribution still holds. So the next theorem Okay, we'll state that if tau is a stopping time, okay, with respect to the sequence of sigma algebras as above, then these processes we defined above evaluated for S replaced by a stopping time. They will be both equal in distribution to a Brownian motion. Okay, so in other words, when you are computing a probability that your process belongs to some set, measurable set in the space of continuous functions, you can either reflect the increments of the process after the stopping time or replace them by a completely independent copy. And of course, here again, I forgot to mention this, that this is on the event that the stopping time is finite. Okay, so maybe more precisely what we want to show is that probability that the process Wi or Wr, so let's say A will be index either I or R, that this process belongs to some measurable set in the space of continuous functions intersected with the event tau is less than infinity. We want to show it's the same thing as the probability that the Brownian motion belongs to A on the event tau is less than infinity. And notice here on the right hand side I do not write it as a product of probabilities. So here the stopping time is expressed in terms of our original Brownian motion W, so they are not independent. Okay, and to prove this, again, first we can reduce this statement to finite dimensional distributions, so we can consider some finite set of times t1, td. As before, we can consider a continuous bounded function on Rd, and then instead of probability or expectation of the indicator, we want to compute the expectation of this continuous bounded function of our process either with index I or R, so with either operation evaluated at times t1 up to td on the indicator that the tau is finite. And the next step is the same as before. So we consider this discretization of the stopping time when we round it up to the nearest dyadic number. So in other words, if we denote as before this function at finitely many times by e tau, so we view it as a function of tau, the first thing we want to notice is that we have convergence when we replace the stopping time tau by its approximation. Okay, and that's where we use the continuity in both variables t and s that I mentioned above. So in this case, this expression is continuous as a function of tau, so as a result you have this type of convergence, and so the above expectation can be approximated by the same expectation evaluated at the stopping time tau n. Okay, and the rest of the calculation is the same. You just look at all the possibilities that the stopping time or the values that the stopping time can take. So when tau n is k over 2 to the n on the indicator, right, that tau n is k over 2 to the n, then because tau n is a stopping time, we know that this event here belongs to the sigma algebra f at the time k over 2 to the n, and at the same time in this first expression fixing the tau, it's like fixing s in our discussion above, so it's like fixing s to be k over 2 to the n. And so as we discussed above, as long as the increments after time s are independent of the sigma algebra up to this fixed time s, it doesn't matter how you define these increments. So they could be either independent copy, or they could be reflection, or they could be the original process. And here in particular, we just go back to the original process and simply write that for each k, you can replace in this definition the above processes just by the original Brownian motion at times t1 td, right, on the indicator that tau n is equal to k over 2 to the n. And when you sum up, you just get a function of the original Brownian motion on the indicator that tau is less than infinity. And that's exactly what we wanted to prove. And I emphasize here again that the Brownian motion and the stopping time are not independent here. The stopping time is defined in terms of this particular Brownian motion. Okay, and this finishes the proof of this form of the strong Markov property that we call reflection principle. And in the second part, we'll take a look at its applications.